Process Analysis. This is the first module of the program and session number 3. This program is consisted of 2 modules and 1 special topic, as you can see from the table. The first module has 4 sub-sessions focusing on discussing process. This is the 3rd session of the first module. During this session, we will discuss a technical aspect of process, including process analysis, with an exemplary simulation and the concept of bottleneck and line balancing. As we discussed, process is a means for converting various inputs into output. Process analysis is trying to understand what the process does, who and why it does specific works, and how effectively it works so that we can explore the improvement opportunities. So we will start with understanding the basic concepts of process analysis. First, the basic unit of process is work center or task center that performs a specific task. For example, work center of copying is a dedicated unit that performs copy work. There could be 1 machine or 2 machines or multiple copy machines that carries out copy work. The entire copy center, which is operating unit, can be consisted of a couple of workstations that are closely related to each other, such as copying, punching, and binding. For now, let's just keep in mind that the workstation is a basic unit of the process. And if you have a couple of workstations, it becomes an operating unit. There are 3 import time concepts, such as task time, throughput time, and cycle time. Task time is the time to complete a task at the workstation. For example, at the copy workstation, the time to complete copying 1 page of paper by using the copy machine. Throughput time is the time that required for a unit of output to pass through an operating unit. If our previous example, copying, punching, and binding, the throughput time include all of waiting times between workstation. The critical time concept that we need to understand is the cycle time. Cycle time is the time interval between outputs from a task or a process. If you stand right next to the copy machine, from the time when you get the first output out of the machine to the time when you get the second output from the machine, and it goes on and on. In other words, the cycle time is the rate at which an operating unit or workstation produce items. For example, my copy machine can copy 100 papers every 1 minute, or my faculty can produce 1 unit of new car every minute. I will show you the details later, but for now, let's just keep in mind those 3 concepts of times. Now, I have 3 more concepts that we want to get to know. The first one is the capacity. Capacity is the amount of output that a specific workstation can produce during the given time. So, how many copies that the copy machine can copy in 1 hour? If a machine can copy 100 papers per minute, the machine can copy 6,000 papers in an hour. So it is an hourly capacity of the machine. If the copy center runs 5 hours per day, the capacity of the machine per day will be 6,000 paper per hour multiplied by 5 hours equals 30,000 papers per day, for example. So the capacity is determined by the available time and the rate of producing output at a workstation. Conceptually, bottleneck is a workstation with the lowest capacity causing work to pile up and restricting the overall speed and throughput of the entire process. You might have an experience that you had to wait because of the slow service station. For example, when you arrive at the hospital to see a doctor, you finish the registration of the arrival with hospital administration, but you need to wait for a long time to actually see your doctor. In this case, doctor is the workstation. That is a bottleneck that has the slow rate of taking care of a patient. As a result, it becomes the lowest capacity of the entire process. Once you see a doctor, you can get your prescription and pay and go quickly. An important fact is that the bottleneck capacity determines the process capacity. In the picture, let's say that you are trying to push some amount of Play-Doh to a pipe, where the beginning part of the pipe has narrow hole and the rest of the pipe has wide hole. If you push the Play-Doh into the pipe, it will go through the narrow entry part of the pipe and will go through with the same share of Play-Doh for the rest of the pipe, since the entry part of the pipe has narrow hole. Only limited Play-Doh will go through and the rest of the pipe. You will have the same shape and amount of Play-Doh. Likewise, in a process, if there is a bottleneck which has the lowest capacity, the entire process capacity will remain same as the bottleneck capacity. Since the capacity is determined by the rate of workstation, the bottleneck speed of work determines the entire speed of the process, which is the cycle time. Since this is a confusing concept, I will walk through a simulation with you to better explain these concepts with a visual presentation. Let's say that there are 3 workstations such as copying, punching, and binding. Each workstation has task time of 1 minute. That means it takes 1 minute to perform each work at the workstation. And there are a stack of raw materials, here stack of papers. Assuming there is no delay between workstation and deliver, the earliest time that the first worker at the workstation 1 can pick up 1 unit of raw material is time 0. Since the task time is 1 minute, after 1 minute, the work at the first workstation will be completed. Then, the worker at the second workstation can pick up the output from the first station at minute 1, again assuming that there is no delay in delivering materials between each workstations, and complete its work at minute 2. Finally, the worker at the third workstation can pick up the output from the second station at minute 2 and complete its work at minute 3. If you stand at the end of this process, you will get the first output out of this process at minute 3. Let's do one more round. Worker at the workstation 1 can pick up another raw material. After the first worker complete the first paper, he or she can pick up another unit of raw material at minute 1 and complete its work at minute 2. And it repeated its task. And one more time. Now you have the second output that came out of the process at minute 4. Let's run this one more time. Then, the third output from the process can be produced at minute 5. Now let's revisit those 3 time concepts. First, task time. Task time is the time to take to complete a specific task at each workstation. In this case, it is equally 1 minute at each workstation. Now, you got the first output from the process at minute 3, and the second at minute 4, and the third at minute 5. Even if you run this simulation continuously, the time gap between each of output coming out of this process will not be changed, and it is every 1 minute. So the cycle time of this process is 1 minute. Since the line is balanced with equal task time at each of workstation, there is no bottleneck. As a result, the capacity of each workstation is exactly same, and thus the process capacity is same as well. Since the cycle time of the process is 1 minute, if you have 1 hour, which is 60 minutes, you can complete 60 copies per hour. And if you have 5 hours, your capacity will be 5 hours multiplied by 60 equals 300 papers per 5 hours. Now, let's have a different process setup. As you can see from the slide, the task time of the first workstation is still 1 minute, but the task time of the second station is now 2 minutes. And again, the task time of the third station is 1 minute. On purpose, I make the second workstation with a longer task time, so it becomes a bottleneck. Again, let's say that there is a stack of raw materials. Again, assuming there is no delay between workstation and deliver, the earliest time that the first worker at the workstation 1 can pick up 1 unit of raw material is time 0. Since the task time is 1 minute, after 1 minute, the work at the first workstation will be completed. Then, the worker at the second workstation can pick up the output from the first station at minute 1 and complete its work at minute 3 because it takes 2 minutes. Finally, the worker at the third workstation can pick up the output from the second station at minute 3 and complete its work at minute 4. Now, if you stand at the end of this process, you will get the first output out of this process at minute 4, different from the first simulation. Let's do one more round. Worker at the workstation 1 can pick up another raw material. After the first worker complete the first paper, he or she can pick up another unit of raw material at minute 1 and complete its work at minute 2. Now, when would be the earliest time that the second worker at the second workstation can pick up the raw material coming out from the first station? What do you think? Yes, it is minute 3, not minute 2, because the second worker in minute 2 still working on the first unit, if you look at the first line of this simulation. And it can complete its work at minute 5 because it takes 2 minutes. Now you have 1 minute waiting time in front of the second workstation, which is a bottleneck, and this is typical phenomenon. Now you have the second output that came out of the process at minute 5 at the third workstation and complete its work at minute 6. The second output out of the entire process came out at minute 6, and the time gap between the first one and the second output is now 2 minutes. Let's run this one more time. Then the third output from the process can be produced at minute 8. Different from the first simulation, the task time for the second workstation is 2 minutes, which is not equal to the other workstations. Now, you got the first output from the process at minute 4, and the second at minute 6, and the third at minute 8. Even if you run this simulation continuously, the time gap between each of output coming out of this process will not be changed, and it is every 2 minutes, and it is equal to the task time of the second workstation, which is the bottleneck station. So the cycle time of this process is 2 minutes. The line is not balanced. As a result, the capacity of each workstation is different. At the workstation 1, you will get output at the rate of every 1 minute. But at the second workstation, you will get the output at the rate of every 2 minutes. If you have 1 hour, the capacity of the first workstation is 60, but the capacity of the second workstation is 30. Since the cycle time of the process is 2 minutes, if you have 1 hour, which is 60 minutes, you can complete 30 copies per hour. And if you have 5 hours, your capacity will be 5 hours multiplied by 30 equals 150 papers per 5 hours. Let's think about the capacity. The process cycle time for the first process was 1 minute, and the process cycle time for the second one was 2 minutes. What is the capacity of the first process? In other words, if the speed of producing output for the first process is 1 output every 1 minute, how many product can the process produce if you have 1 hour? Simple math. 60 minutes divided by 1 minute of cycle time is 60 output. While the first process can produce 60 outputs per hour, the second process only produces 30 outputs per hour. Why? Because the process cycle time for the first process is much shorter than the second one. This is the relationship between cycle time and capacity. The shorter cycle time, the bigger number of outputs. That is why we are interested in reducing cycle time. Now let's think about how to reduce the cycle time of the process so that you can produce the same amount of output as the first process does. The capacity is only 50% compared to the first simulation with the perfect balanced line. This is because of the bottleneck workstation. Therefore, the bottleneck workstation has the lowest capacity due to the longest cycle time. That determines the entire process cycle time and its capacity. Now, since we have a non-balanced line, let's try to make the line balanced. Although there are a number of options that we can try, let's hire 1 more person and buy 1 more machine for the second work center. The task time for the second work center still 2 minutes. Assuming those 2 workers work independently, which means each person handle each machine and work separately, not sequentially together. What is the task time of this workstation? Still 2 minutes, because it still takes 2 minutes to complete a job for each worker. But what about the cycle time of this task? Again, cycle time is a mathematical concept of the speed. In other words, the rate of production. So what is the rate of the speed in the second workstation? Mathematically, 2 outputs every 2 minutes. Again, you can say that 4 outputs every 4 minutes. But as we discussed, we want to express the cycle time per equal unit of the time, which is 1 minute. 2 outputs per 2 minutes equals to 1 output per 1 minute mathematically, isn't it? Now the cycle time of the second task is 1 minute as the cycle time for the other tasks resulting in the process. Cycle time is 1 minute. Therefore, the capacity for this balance process will be 60 outputs, same as the very first process from my presentation. Therefore, understanding the concept of different time measurement and bottleneck is very important. You can have more capacity just balancing the line with an equal cycle time. Again, balancing the process is getting rid of the bottleneck, which has the lowest capacity and longest cycle time in the process. The bottleneck not only reduces the capacity of the process, but also increases unnecessary weight and inventories. It also creates some idle capacity, which is another type of wastes of your resources. One additional important fact here is the throughput time. If you see the second process example with a bottleneck, the throughput of the first unit was 4 minutes, but it becomes 5 minutes. From minute 1 to minute 6, including waiting time of 1 minute. Then it became 6 minutes with the 2 minutes of waiting time. If you continue to run this simulation, the throughput time of each unit will get longer. Again, this is because of the bottleneck resulting in accumulating waiting time in front of the bottleneck workstation in the process. Therefore, the throughput time is not only the summation of the task time of each workstation, but it depends on the number of work-in-process inventories along the process. In sum, the process analysis can give us various improvement opportunities. The critical point here is the bottleneck. Because the bottleneck determines process cycle time and capacity, it is important to identify bottleneck and get rid of it to achieve the line balance of a process.